Continuing on in our structural estimation workflow, we're now going to talk about how we estimate the model. We've developed the model, we've tinkered with it to understand how it works, and now we're trying to actually estimate the parameters of the model given the data that we have. The key with structural estimation is that most structural models require nonlinear estimation. So this is going to be things like maximum likelihood estimation or generalized method of moments or simulated versions of these estimators. And when we're doing this nonlinear optimization, the starting values are going to be critical to whether we actually get convergence of our estimator or of our estimation algorithm. If we just initialize with random starting values like uniform 0, 1 for every parameter, that's going to very likely give us poorer results. And so we need to keep that in mind. So the question is, what's the best way to get starting values that make sense? And one thing that Michael Keene suggests that I definitely agree with is to start simple and to calibrate the parameters by hand. This somewhat relates to our previous video about understanding how the model works, where we're tinkering with the parameter values to see how that changes the solution of the model. Here, we want to start by calibrating parameter values for the constant terms that will match the average values of the variables in the model. So for example, I can calibrate a value for beta 0 that's going to exactly make it so that the prediction of my model will match the actual data on average for the average log wage. And I can do the same thing for the share of people choosing school, the share of people choosing employment in the second period, and so forth. Then, once we get those working, then we can gradually add other aspects to the model. So we can add the coefficient on schooling in the wage equation. How is that coefficient identified? We need to compute the correlation between schooling and wages, and that correlation is going to pin down that parameter value, and then we can compare that in the data with what was the correlation between schooling and wages. And we can do this with all of the parameters and moments of the data that are entering our model. And this is going to help with starting values, which is going to help with performance of the estimation algorithm. Some other tips. One thing I like to do is to just start by estimating a model with only intercepts in every equation. That's kind of similar to what Michael Keene's advice is. Another thing I like to do, which is to also verify that the data is being correctly read in, is to estimate very simple regression models in multiple different languages. So whichever one I'm in, so if we suppose that I'm using Julia to estimate my structural model, then I might use R or Stata or SAS to estimate a simple regression model and make sure that the sample size and all of the coefficients are numerically identical because it's the same data, or it should be the same data being read into both programs. Another thing that can be helpful is to look at code from published papers that are similar to the one that you're working on. That can give you clues about how estimation should be structured, what reasonable starting values are, and so forth. So now that we've kind of talked through some of these finer points of estimation, let's go through how to do this in Julia with, again, this very simple stylized example of the schooling choice model. So we have some Julia code here. We can estimate the log wage equation very simply, and we get these coefficients. Then we can get predicted log wages that are going to enter our utility function later. We can also look at the R squared and the root mean squared error and so forth. We can also do a logit of, is the person a college graduate, based on the variables that enter the U1 equation. And we see that having a parent who went to college is a strong predictor of the child attending college and graduating from college. And then this EFC variable, which we haven't really gotten into how it's created, that seems to be positively correlated with college completion. Now, we didn't really say what that was, so we're not sure what the sign of this coefficient should be. And then we can do the second utility function, the U2 estimation, where we're regressing employment on expected log wage and number of children. And here we've baked in the decision of what the actual schooling decision was, because we plugged in the college graduate status back in this equation. And we see a strong relationship between having a higher wage and choosing to work. I think that makes sense. And then having more kids is negatively correlated with working. So again, we don't really have a theoretical definitive sign. It's theoretically ambiguous, and so we shouldn't probably put too much stock in at this point what that coefficient should look like. So that's a little bit about how we estimate the model, or at least how we work towards estimating the model. Obviously, there's a lot of complex, complicated, difficult methods, some econometrics that will give you a headache that might be involved, and we'll cover those in future videos. But for now, we're just trying to focus on the workflow, and so we're keeping it pretty high level. So hopefully you found some value out of this video, and if so, hopefully I'll see you in the next video where we'll talk about validation and counterfactual policy simulations.